To explain the mechanism of reciprocal regulation of glycolysis and gluconeogenesis, we have to know that metabolical processes in our organism have strict hormonal regulation. Both glycolysis and gluconeogenesis are regulated by insulin and glucagon. In glycolysis, glucose is degraded to pyruvate. In gluconeogenesis, pyruvate is used to produce glucose. Insulin stimulates glycolysis, glucagon stimulates gluconeogenesis. And despite their opposite directions and totally opposite regulation, these two processes have very much in common. Recall that in glycolysis, glucose initially is phosphorylated to glucose 6-phosphate, and now this trapped glucose is converted to fructose 6-phosphate that by enzyme phosphofructokinase 1, PFK1, is converted into fructose 1,6-bisphosphate. In gluconeogenesis, glyceraldehyde 3-phosphate and dihydroxyacetone phosphate produce fructose 1,6-bisphosphate, and then enzyme fructose bisphosphatase 1, FBPase1, cleaves this phosphate group, and fructose 6-phosphate released. Then fructose 6-phosphate converted initially into glucose 6-phosphate, and then phosphate group is cleaved and thereby glucose is formed. From this point we will call fructose 1,6-bisphosphatase FBPase. So these two processes occur in opposite directions, and processes that occur in opposite directions cannot be active at the same time. If glycolysis is activated, gluconeogenesis must be inhibited, and vice versa, if gluconeogenesis is activated, glycolysis is inactive. Such regulation called reciprocal regulation. And we see that both these processes occur in the cytoplasm and they have the same intermediate metabolites, including fructose 6-phosphate and fructose 1,6-bisphosphate. And this reciprocal regulation is provided basically by shunting of intermediate metabolites from one pathway into another. And shunting of intermediate metabolites from one process directly into another is basically the fastest regulation possible. The logic here is that, for example, after the intake of high carbohydrate meal, blood glucose level is high, and there is no point to synthesize additional glucose molecules. Much better option is to degrade glucose to pyruvate, and pyruvate can be converted into acetyl-CoA that can be used in fatty acid synthesis. So, for example, in the well-fed state, glycolysis must be activated and gluconeogenesis must be inhibited. But during hypoglycemia, the absolute priority is to maintain blood glucose level. So in hypoglycemia, all common intermediate metabolites have to be used for glucose production. So with low blood glucose level, gluconeogenesis is activated and glycolysis must be inhibited. And gluconeogenesis results in production of glucose, and then glucose from liver or kidney tissue will enter into the blood, and with this liver and to a lesser extent kidneys maintain normal blood glucose level. And which pathway will be activated determine hormones, insulin and glucagon. So how these processes are regulated? The concept is that the activity of PFK1 as well as FBPase1 is regulated by fructose 2,6-bisphosphate level. High fructose 2,6-bisphosphate levels stimulate PFK1, thereby increasing glycolysis, and simultaneously high fructose 2,6-bisphosphate level inhibits FBPase1, thereby inhibiting gluconeogenesis. And vice versa, low fructose 2,6-bisphosphate levels stimulate FBPase1, thereby stimulating gluconeogenesis, and simultaneously inhibit the activity of PFK1, thereby inhibiting glycolysis. And the concentration of fructose 2,6-bisphosphate is regulated by two enzymes. The first one is phosphofructokinase 2, PFK2. PFK2 converts small amount of fructose 6-phosphate into fructose 2,6-bisphosphate. As a result, the level of fructose 2,6-bisphosphate increases. And also the second enzyme that regulates fructose 2,6-bisphosphate level is fructose bisphosphatase 2, FBPase2. FBPase2 degrades fructose 2,6-bisphosphate into fructose 6-phosphate. So FBPase2 decreases the level of fructose 2,6-bisphosphate. Actually, PFK2 and FBPase2 are two different domains of one enzyme. So because domains are different, to simplify, we can imagine that it's two separate enzymes. So we see that PFK2 increases fructose 2,6-bisphosphate level and FBPase2 decreases fructose 2,6-bisphosphate level. And the key concept here is that the activity of both these regulatory enzymes is controlled by hormones, insulin and glucagon. Insulin stimulates the activity of PFK2 and simultaneously inhibits the activity of FBPase2. So production of fructose 2,6-bisphosphate increase and degradation decrease. So the level of fructose 2,6-bisphosphate increase. And increase in the level of fructose 2,6-bisphosphate stimulates the activity of PFK1 that converts fructose 6-phosphate into fructose 1,6-bisphosphate, thereby activating glycolysis. And simultaneously, increase in fructose 2,6-bisphosphate level decreases the activity of FBPase1. Decrease in activity of FBPase1 causes decrease in conversion of fructose 1,6-bisphosphate into fructose 6-phosphate, thereby inhibiting gluconeogenesis. This results in accumulation of fructose 1,6-bisphosphate that is shunted into glycolysis where it's used for pyruvate production. In contrast to insulin, glucagon stimulates the activity of FBPase2 and simultaneously inhibits PFK2. So in this case, degradation of fructose 2,6-bisphosphate prevails over production. This results in decrease in fructose 2,6-bisphosphate level. Decrease in fructose 2,6-bisphosphate level stimulates the activity of FBPase1, so the conversion rate of fructose 1,6-bisphosphate into fructose 6-phosphate increase, thereby this stimulates the activity of gluconeogenesis. And simultaneously with decrease in fructose 2,6-bisphosphate level, the activity of PFK1 decrease, thereby conversion of fructose 6-phosphate into fructose 1,6-bisphosphate decrease. This results in accumulation of fructose 6-phosphate, and fructose 6-phosphate is shunted into gluconeogenesis. So let's take the real situation. Let's assume that we intake high carbohydrate meal, so after glucose absorption, glucose level in the blood increase. Increase in blood glucose level stimulates secretion of insulin and decreases secretion of glucagon. So in this case, the hormone that acts is insulin. Insulin stimulates PFK2 and inhibits FBPase2. This results in increase in fructose 2,6-bisphosphate level. This stimulates PFK1, thereby more fructose 6-phosphate molecules will be converted into fructose 1,6-bisphosphate molecules, so the activity of glycolysis increase. And increase in fructose 2,6-bisphosphate level inhibits FBPase1, thereby conversion of fructose 1,6-bisphosphate into fructose 6-phosphate is inhibited. Inhibition of gluconeogenesis results in accumulation of fructose 1,6-bisphosphate that undergo degradation in glycolysis. And for example, if blood glucose level decrease, hypoglycemia stimulates secretion of glucagon and inhibits secretion of insulin. So in this case, hormone that acts is glucagon. Glucagon inhibits PFK2 and stimulates FBPase2. This results in decrease in fructose 2,6-bisphosphate level. This stimulates FBPase1, thereby more fructose 1,6-bisphosphate are converted into fructose 6-phosphate, so the activity of gluconeogenesis increase, and also decrease in fructose 2,6-bisphosphate inhibits activity of PFK1, thereby conversion of fructose 6-phosphate into fructose 1,6-bisphosphate decrease. So inhibition of glycolysis results in accumulation of fructose 6-phosphate that is used in gluconeogenesis. So basically it's a general principle of reciprocal regulation that is used in glucose metabolism.